to hit start recording this time around. So the recording has also started now that everything seems to be working. Good. So welcome back to the last week of algorithms and data structures, a week that is going to be, well, different than I originally planned, but we'll see what we can make work regardless. This week is going to be about P versus NP as announced. So we have a few more things to talk about today. In this course, I've already taught you quite a lot, or at least I hope I did. Lists, stacks, queues, heaps, trees, maps, and graphs, a bunch of algorithms, a bunch of graph algorithms, and today, finally, we get to talk about that ultimate challenge in computer science of P equaling NP. And that's it in terms of lectures. So tomorrow we will have one more tutorial in which you can answer, or you can ask any questions you have, and I will try to answer them. More about that in a moment. There will be 2 more labs this week, and next week there will be 1 exam. So let's start by talking a little bit about that. Hopefully you've all read the announcement that I posted last Friday. So the following information should not be new to you, but just in case, there is an exam next week. That will be 1 exam. This will be a take-home exam that you should complete between 9 and 11 in WebLab. The regular exam time, and also in WebLab as was planned, the only difference is that you will be doing it from home. Then I will be grading this exam as quickly as I can. I hope to do all of that on Monday, so that Monday at 5 I can let you know whether or not you passed the exam. Then, for those of you that scored a passing grade on the weighted average of the midterm and this take-home exam, we will have to do an oral exam to verify that indeed you did this exam on your own strength. And if you pass this oral exam, you will get a passing grade for the course. This exam, like I said, it will be just 1 exam replacing the 2 exams originally scheduled, meaning this exam will contain both implementation as well as analysis questions. In my design of the exam, my plan, my advice/plan is that both should take you about 1 hour to complete. So both should be about 1 hour of your time. There will be no guideline, or there will be no enforcement of this guideline, right? So if you want to spend 1 hour and 50 minutes on the implementation and only 10 minutes on the analysis, or the other way around, that is possible, but I would not recommend it, right? If you are stuck on the implementation, take a look at the analysis first. This is the reason originally that I split the exams, because I noticed that computer science students struggle with this, right? On the implementation, you get immediate feedback, so you know you might not have passed all the spec tests yet. So it's very easy to get stuck in those, but don't, right? It's 1 hour for implementation, 1 hour for open. That is my recommendation. Okay, and as I mentioned, tomorrow's tutorial is all for you guys to decide, guys and girls and whatever other genders there are, for you to decide what we are going to talk about. Right, so are there specific questions you'd still have? I can answer those. Are there algorithms you want us to take another look at, etc., etc. There will be a question today at the end in feedback fruits where you can let me know what you want to discuss tomorrow. Now, I see some questions are already trickling into chat. Excellent, I'll answer those now. If you have any other questions about the exam next week, this is your moment to ask them. I have 1 question to ask you in a moment as well. We'll get to that in a second. So let me start by answering these 2 questions in chat. From Ait, how will the grade be weighted? Will the single exam be 60% of your final grade? So Ait, as I mentioned in the announcement, the final grade for this course will simply be a pass or a fail. There will not be a grade out of 10. To determine whether you can get the pass, whether you qualify for the oral exam, right? I will indeed be using a 40% weight of the combined midterm grade and a 60% weight on the final exam grade. And if that weighted average is a passing grade, we do an oral exam, and if you pass that, then you pass the course. You pass it, you don't get a grade for it, you get a voldoende, a pass in Osiris. So you get your 6 CC, but unfortunately no grade. This has been decided in collaboration with the Board of Examiners. Daniel is asking, can we use the lab assignments during our test, since it's an open book test? Yes. Do I like that? No, but that's the way it is. So yes, WebLab will not be closed. You can look at other assignments there. Alfie is asking, oh, by the way, when I've answered your question, or I think I've answered your question, so when I move on to the next one, could you please let me know in chat whether I indeed answered it? So Ait and Daniel, did I answer your questions? As you'd let me know that, I will move on to Alfie. Will the exam be more difficult as it is an open book test? It's a tough question, right? Will it be more difficult? No. Will it be different? Well, a little bit. I'm not going to ask you something that you can literally look up in the book, whereas previously I could at least have considered it. That being said, if you take a look at the midterm exam of this year, as well as at the end terms of last year, the example and the real end term, you will find that there were very few questions already that could be looked up in a book, right? So will it be more difficult? I hope not, right? It's not my intention to make it more difficult. I will, of course, try to ask you questions that you cannot literally look up in the book, or in the WebLab implementation assignments, or in the WebLab analysis assignments. For the record, anything other than the book and WebLab is not allowed, right? So you are not allowed to use Google, Wikipedia, or anything else to answer these questions. Can I check that? No. But if I find out during the oral exam that you have no idea what you're talking about, sorry for putting it that bluntly, but then I will take the appropriate steps. Which means failing you for the exam and reporting you to the Board of Examiners. Right? So make sure you do the exam on your own strength, and then you have nothing to lose. Then it's just a regular exam in which you happen to be allowed to use the book and the WebLab assignments. I hope that answered it, Alfie, so I'll move on to the next one. Can we also use the provided answers to the lab and tutorial sessions? Are we allowed to use the book? You are allowed to use the book. Are you allowed to use the provided answers to the lab and tutorial sessions? Yes. So I hope that answered yours, Andre Aaron. Daniel again, so questions like implement Dijkstra, etc. are off the charts now, since we can just copy and paste it. Well, likely yes. I will not ask you literally implement Dijkstra, because indeed you could copy and paste it. I could ask you to implement Dijkstra with a twist. I could ask you or I could give you a general problem and tell you solve it, and you'd have to figure out that you need to use Dijkstra, right? So it's not impossible for me to ask you about Dijkstra. I'll just have to ask it differently. I hope that answered the question, Daniel. Shumpun, how does the fact that the grade is either a pass or fail influence whether someone passes cum laude / gets into the honor program? Good question. This is something that I also discussed with the Board of Examiners, and that many of my colleagues are also asking, because many of the students are asking us. If you get a pass or fail for a course, this course is not included in your average, meaning that other courses get a slightly higher weight in the computation of the average. I've been told to tell you this. If you still want a grade out of 10 for this course, you are welcome to try just the exam next year. It is not a solution I particularly like, but that is, I'm afraid, I'm the only option I can give you. So the pass-fail will not count towards a cum laude or honors program, but that does mean that other grades will get a slightly higher weight in this computation. And therefore, if you think you can score a 9 for this course, I might imagine you want that 9. Unfortunately, the only thing I can do is ask you to take the exam next year as a result. I don't like it much either, but that's the answer I can give you, Shumpu. Alwin, is the example test on Brightspace still a good example of what kind of questions you can expect? Yes. I can be brief about that one. Yes. With, like I said, the exception that if there is a question in there that you could really look up in the book, I will likely not ask it. And it is likely that you will get more open questions instead of multiple choice questions. So there could be multiple choice questions in the analysis part, but it's likely there won't be. Can we also use the slides, asks Si Jing. Yes, slides are also available for you. Or you're allowed to use them, I should say. Other questions about the exam? And for Daniel, Shumpum, Shumpum already replied. For Daniel and Alwin, could you let me know whether I answered your questions? Alwin says yes, that's good. And Daniel as well, excellent. Okay. I see no other questions at the moment, or unless I missed one, but I don't think so. So what I suggest we do is that we get started with the content of today. If any other questions about the exam pop up at any time, please write them down for yourself, and immediately after the break, I will answer the next bunch if there are more. All right, good. Then let's get to talking about P versus NP, our topic of today. I have feedback fruit set up again as well. The code today is QLZ, which I will also post in chat. There we go. And let's get started. So last week we talked about finding minimum spanning trees. We talked about Prem-Yarnik and Kruskal, which both had pretty good runtimes, were efficient algorithms to find a minimum spanning tree. Which means that on our list of problems that we were solving for the Dutch railway network, we are almost done. We have solved the first question, what cities can you reach, by using BFS or DFS. We've solved the second question by using Dijkstra or A star to find the quickest way to get from A to B. We have found an answer to the third question, what is the best way to connect new stations, by looking at minimum spanning tree algorithms. And we could use this to build a network from scratch, or if we already have an existing network, maybe we could use an algorithm to see where to connect a new city. And now it's time for this final question. How can we quickly tour the entire country? And already last week I gave you an introduction. I introduced the problem of the traveling salesman. And the traveling salesman is a problem that I told you I have no solution to. I don't know the best way to solve this problem. In fact, I don't know a feasible way to solve this problem at all. And that's going to be the topic of today. Today we get to talk about the real question in computer science. The real thing each and every one of us should be working towards, if you ask me. Of course, I'm only one person, and it's a good thing not everyone listens to me. So what is that question? Well, so far we have looked at how do I solve this problem efficiently, and for all the problems we've seen so far, there has always been an efficient solution. Binary search was a great improvement over a linear search. The closest pair of points algorithm that we discussed was a great improvement with n log n over n squared. BFS, DFS, and Dijkstra are our beautiful examples of efficient graph traversals. And Prem-Yarnik and Kruskal last week showed us efficient ways to get a minimum spanning tree out of a graph. But does that mean that we can solve all the problems in the world? Well, perhaps this is obvious, but no, we cannot. In fact, in a course called Automata, Computability and Complexity, amazing course, CSE 2315 for next year, if you want to do another extra course, why not? We can show that there are problems that have no solution. We can never write an algorithm to solve the problem. A famous example of this is the halting problem and the word acceptance problem. Two problems that we can show cannot possibly have an algorithm to solve them. Now that's very nice, but that's also a bit, yeah, okay, if we can't solve them, then we shouldn't try, right? If we can prove they cannot be solved, and we have proven this, then there's no point trying. But there is also an interesting class of problems that is solvable, In automata or in computability theory, we call this decidable. They are solvable problems, but these we can distinguish into different categories. There are easy problems to solve, and there are hard problems to solve. And this distinction is what I want to look at with you today. Now, this difference can be a very small difference. I can change just one tiny thing in a problem, and it suddenly becomes hard, whereas before it was easy. And to show you this, I want to take a look at some examples together with you. And I've based these on slides that my colleague Kees Witteveen originally created for the course of complexity theory. And I thought, okay, well, originally these were all about some dating agency that was setting up a new business model, but I thought, well, let's try to make it a little bit more up to date with the current situation. So, imagine that you have a graph in which you want to track interactions between people. For example, let's say that we want to model what's currently going on in the world with the epidemic raging on. We would like to know who has been interacting with who so that we can prevent further spread of this epidemic. So what do? We create a graph. Every person becomes a vertex in the graph, and there is an edge between x and y if x and y have recently interacted or have interacted. The recent becomes a little bit vague, right? Because that would mean the graph would change over time, stuff like this. Let's say we take a snapshot, x and y, this edge exists when two people have interacted. So that's the idea. I have this interaction graph. Now, given this graph, I might have a number of questions that I would like to answer. For example, if I find out that a person has the virus, I would like to find the largest set of nodes that I need to warn that they have interacted with someone who has the virus. So, given a vertex, I want to find the largest set that is connected to this vertex. My question is simple. Is this problem easy or is this problem hard? Now, I haven't exactly defined easy and hard yet. That's intentional. Let's see what you intuitively think. So our code today, QLZ, and Feedback Fruits is happy to hear your answer. And let's see. Overwhelming majority with 78% for easy. And you are right. In fact, we've already seen how to do this, right? All we need to do is find all the neighbors of a node. Well, depending on how we've structured our graph, this is an easy problem. If I have just a list of edges, worst case, I need to go through all the edges once, and I have my answer. So that seems like it might be easy to do. Okay. Now let me change this slightly. Instead of knowing that when one person has been infected, I want to know the largest set of nodes connected to that one person. I now want to find the largest group that has been together recently, right? Social distancing is very important nowadays, but still there might be some people that have decided to all come together in a large group. This is something we want to avoid. So we want to find out what is the largest group that recently came together. And what do I mean with that? I'm looking for a group where every person in that group has recently interacted with every other person in that group. So for example, if it turns out that the largest group is a group of 3 people, then A will have interacted with B, B with C, and A also with C. In the graph, they form a little triangle, if you will. Then For a group of 4, this fourth person would have interacted with all 3, and all 3 with him or her, etc. So my question is, finding this largest set of people that have all recently interacted, easy or hard? Again, Feedback Fruits is happy to hear your answers. Okay, and let's see. Either you see where I'm going with this, or you're working, or you have a good intuition for this. 3/4 of you say this problem is hard, and you're right. So what do I mean with this problem to be hard? Well, what I mean is that the best solution I've got to solve this problem takes exponential time in the size of the graph. Meaning, if I make the graph just one node larger, the time required to solve the problem will immediately become twice as big, or at least a constant factor as big. So making it additively bigger will make the runtime multiplicatively bigger. Right, well, you know what exponential time is. You're mathematician, so I shouldn't need to explain this to you. Now this problem also has a nice name. We call it the max clique problem. A clique is a set of nodes that is all connected to each other, and we're now looking for the maximum clique of a graph. Okay, let's do a couple more. We have the orders to remain in isolation, but well, isolation can be very lonesome. So what I think might be a good idea is, how about we try and put people together in pairs. We isolate them in pairs. But of course, we should only put them with someone who they've interacted with. No need to look for extra risk. So my question is, how many people can I put in isolation together? Right? So if I split people, or if I put people in isolation in pairs, how many people can I put in isolation? Again, my question is simple. Is this question easy or hard? And Feedback Fruits is happy to hear your answer. All right, let's see. Ooh, getting too close to a 50-50 split now. Very nice. But a small majority for hard. Well, it was a bit of a tricky question, because I haven't shown you an algorithm to do this. With the current tools available, well, we could get pretty close, but I have never shown you a real way to get there. However, as it turns out, this problem is easy. Why is that? Well, there is an algorithm, it was developed in 1980 by Mikali and some others, that can do this in the square root of v times e time. Amazing. I have no idea how it works, but this exists. And this is a fair runtime. An easy solution. An easy problem, therefore. Now let me change this problem just a tiny bit. Instead of matching people up into pairs, I want to put them in isolation in groups of 3, in triplets. And again, I only want to put them in isolation if all 3 of them have interacted with each other. A with B and C, and A and B with C. How many people can I put into isolation together? My question again. Easy or hard? There we go. I got an email, by the way, that my webcam is delayed, so likely we will not be seeing it before the end of this course. So we will have to do with my choppy phone as a cam today as well. Apologies for that. Good. An overwhelming majority for heart. Yes, either you again saw where I was going, or you really are developing a good intuition. I've changed just one thing, right? Instead of groups of 2, I'm now looking for groups of size 3. And suddenly, this problem has become hard. The best algorithm we've got is exponential in the size of g. Meaning that, again, there is no efficient way, that no algorithm that scales well as the input grows larger. Now, this problem also has a name. It's called partition into triangles. And it pops up also, for example, in computer graphics. For those of you who have ever looked into stuff like this, in computer graphics, to render certain 3D images, we often split them into triangles. And as it turns out, partitioning into triangles is a hard problem. Now, there is one interesting observation to make here. This problem, partition into triangles, is hard, but as it turns out, it's just as hard as this problem max clique. If I solve one of the two efficiently, I get the other one for free. Solving one immediately gives us a solution to the other one. More on that later. One last one to wrap this bit up. Imagine that the unimaginable has happened. We have found a vaccination to cure our epidemic. Now, we're asking people to line up for the doctor's office to get their shot. But just in case something goes wrong or it doesn't work or whatever, we want to again make sure that we limit interactions that have not happened before. So we want to line people up in such a way that for every person in this queue, the person in front of them and the person behind them are people they have previously interacted with. My question is just a yes or no question, namely, can this be done? Can I order the people in such a way that they have interacted with the person in front and the person behind them? With the exception, the people at the front and the people at the end, of course, they only need to have interacted with the one other person. Can it be done? My question is this question. Is it easy or is it hard? And let's see what you think. Again, very close to a 50-50 split, but a small majority for easy. Yeah, at first you might think, okay, but this is very similar to some algorithms we've seen, right? Maybe we could use a topological ordering, because that was also about ordering things in some way. But remember, topological ordering only worked for directed graphs, directed acyclic graphs, and this thing is neither directed, and it could also be cyclic. So topological ordering doesn't work. Maybe we could use a BFS or a DFS to see if there is some path through the graph. Sure, but finding a path through all the nodes in the graph, as it turns out, is a hard problem. We call this the Hamiltonian path problem. And again, the best solution I've got requires exponential time in the size of the graph. And just like before, this problem, Hamiltonian path, can be shown to be just as hard as the other two. Solving any of these three problems gives us an efficient solution in an efficient way, gives us an efficient solution for all three of them. So I've shown you now some problems that differ only a tiny bit from things you've seen before or even from each other, some of which are easy and some of which are hard. So why Why do I think this is so important? Well, as it turns out, many problems in the real world are actually very hard. They have no efficient solution that we know of. And without knowing this, it's very hard to find a suitable algorithm. If you decide to use Dijkstra on something that Dijkstra cannot be used for, things are bound to go wrong. Or if you think, this problem should have a solution, you might spend days working on it, only to find that, well, you are not able to come up with a solution. And you could also have taken a little bit of time to think about, okay, but how hard is this problem actually? And you could perhaps prove that the problem is hard, and that therefore, well, finding the solution would not only hopefully get you a promotion within the current job that you have, it would also get you that $1 million I talked about last week. So knowing something about the difficulty of the problem allows us to determine what a suitable algorithm is to solve the problem. And this often goes wrong, because as it turns out, there's many companies out there, many well-intentioned people, who are solving problems with heuristics, approximations, or even probabilistic methods, right? Algorithms that use some randomness to get to an answer, because they think they're solving a hard problem, but actually they're solving an easy problem in an inefficient way. So knowing whether a problem is easy or hard allows you to justify your use of these approximations. If a problem is really hard, if a problem requires longer than the age of the universe, as we saw last week, to solve, then perhaps you can go to your boss and say, well, sorry, I cannot give you the real answer. I can give you an answer in a reasonable amount of time that is at worst 5% off from the optimum. I don't know how much it's off by exactly, but at worst 5%. And your boss is very likely to accept this. Unfortunately, even the 5% is a little bit rare. Commonly, 100% is what we deal with. The optimal solution might be 10. We find something that's twice as bad. So knowing something about the difficulty allows us to find a suitable algorithm. And the suitable algorithm could be, don't bother trying to solve it exactly, use an approximation instead. But beyond that, I believe that studying complexity theory teaches us something that is beyond just computer science. It teaches us something about the very nature of time and space in a way that physics couldn't. It might even teach us something about the nature of human intelligence, but more on that later. So, let's see, I think the next slide's already the intermezzo, but I want to skip that, yes, till after the break. So let's formalize our problem a little bit first. I've talked so far about easy and hard, leaving them a little bit undefined. I want to take a moment to properly define these a little bit. So we have seen a bunch of different algorithms to solve the same problem, right? Dijkstra and A star both solve the problem of the shortest path. Prymjarnik and Kruskal both solve the problem of the minimum spanning tree. And worst case, there was always just try all the options, right? Even for Dijkstra, just try all the different paths. Okay, there's a lot of them, but you could just always try them. These are all algorithms that solve the same problem. So how can we say something about the complexity of that problem? So far, we have only looked at the complexity of algorithms. Dijkstra's algorithm has a certain runtime. A star has the same runtime, but could be better in some cases. Finding all the paths has a horrible runtime, but it has a certain runtime all the same. In the real world, however, I have a problem before I have an algorithm. So what I would like to do is answer this question of how hard is the problem, instead of what kind of complexity does an algorithm have. So how can we do that? Well, consider the problem path. Given a graph with vertices and edges, two vertices S and T, my question is there a path from S to T? This is the path problem. Well, as we have seen, there's multiple options. We could try all of them, That's something exponential, or maybe even a factorial of the number of vertices. Pretty bad. We could use Dijkstra. It doesn't just give us the answer to this question, but it would also give us the shortest path from S to T. Or we could use a DFS or BFS, which does exactly this, right? It answers the question, is there a path from S to T? It doesn't give us guarantees on the shortest or anything like that, but it does give us a path. 3 algorithms for the same problem, 3 algorithms with very different complexity. So what do? Well, we say the complexity of a problem is the time required by the best algorithm to solve the problem. So for example, for path, assuming there is nothing better than BFS or DFS, the complexity of the problem would be V plus E. But that's not a definition that's great. Any idea why not? Why is this not a definition that's great? Yeah, Shumpum, you're absolutely right. So you still need an algorithm to say something about the problem. So we need to solve it first before we can actually classify it. Very true. But I was actually hinting here at the answer, or trying to get to the answer, I should say, of Om and Bro. So Shum, you're actually absolutely right. We still need an algorithm before we can say something about the problem. But even when we have an algorithm, how do I know it's the best algorithm? Right? So as Om and Brouw say, who knows whether we found the best solution? We may have found a solution, but in order to know that it's the best one, I'd have to think somehow about all other possible solutions, things I haven't even come up with yet, and show that they can't exist, or show that they are always worse than the one I've created. That's tricky, that's real hard. In fact, there are very few problems for which we've successfully done this. One example for which we have successfully done this is sorting. We know that a comparison-based sorting method, so a method that compares different elements, can never be done quicker than n log n. This was a difficult proof, but this has been shown, which is why merge sort is the best. We can never beat merge sort in terms of time complexity when it comes to comparison-based sorting algorithms. But for many other problems, for instance the shortest path problem or even the path problem, such bounds are very hard to create, if at all possible. So yeah, proving we can never do better is not trivial. Well, fortunately we found a way around that. We've decided to split these problems into certain complexity classes. And in these complexity classes, the exact runtime of an algorithm doesn't really matter anymore. One of these classes is the class P, and another is NP. And these are the two problem classes that I want to look at with you. Now, although they can talk about problems like what is the shortest path, we will focus only on decision problems, problems that have a yes or no answer. So for example, for our path problem of just now, the question was, is there a path from S to T, right? Not what is the path, but is there a path? And we'll see more examples of that soon. Now, with that in mind, P is the set of all problems that can be solved in polynomial time. And that's great. Why? Well, because as soon as I found my BFS algorithm that requires V plus E time, some polynomial in terms of the input, I'm done. Sure, maybe it could be done in V time, maybe it could be done in E time, maybe it could be done in log V time, I don't care. I found a solution that it requires polynomial time, therefore the path problem is in the class P. So path is in there. What else is in there? Could you give me more examples of problems in P? Problems that can be solved in polynomial time. Very nice, Shumpum. Solving a Rubik's Cube. Yes. especially for the 3 by 3 by 3 variant, this is definitely a problem that can be solved in polynomial time. Yeah. Anything else? I'll have one or two more if you have them. No. Sorting, yeah. A function that just returns 5. Yeah, these are all examples of things that can be solved in polynomial time. For sorting, again, we would have to figure out some way to make it a decision problem, right? Because we're only focusing on decision problems. So maybe we could ask, given a list K and a list L, is L the sorted version of K, right? This we can check in polynomial time, so we can return yes or no. A function that returns 5, yeah, is f a function that returns 5. We could check that in polynomial time. So we could output yes or no in polynomial time. Yes, I was thinking some stuff like this. Is item x in the list L? We can do that in linear time. Is there a path from S to T in this graph? We can do that in linear time. Is there a path from S to T in this graph with at most length k? Yeah, we can solve that in linear time as well. You're mentioning Sudoku. And 9 by 9 Sudoku, yes. And n by n Sudoku, well, given a solution, we can check the solution. But just, here is the Sudoku. Is there a solution? We cannot do in polynomial time. Or at least, and we'll talk about this a little bit more soon, we think we cannot do it in polynomial time. So that is the other class of problems, the class NP. And the class NP is the set of all problems for which solutions can be verified in polynomial time. So, given a solution, we can check if that solution is valid. For example, if we take TSP from last week, the question was, is there a simple cycle through all vertices such that the total length, so with this, okay, what is a simple cycle through all vertices with the smallest total length? But if we make it a decision variant, is there a simple cycle through all vertices with a total length less than or equal to k? Now, if you give me one of these cycles, I can check that this is indeed a cycle through all vertices with a length smaller or equal to k. Here we go. You give me this path pi, this cycle pi. I label them v1 through vx. First I check, is it indeed a cycle? And then I check, are indeed all of these consecutive vertices connected by an edge. I compute the sum of the weights of these edges, and I return whether this is smaller or equal to k. So indeed, I can verify this in polynomial time. I'm going to skip this question, just show you the answer. We can do it in veta v time. Great, I don't care. It's in polynomial time. And the question we ask, so TSP is therefore in NP, right? We can verify a solution in polynomial time. Yes. Let me do the intermezzo now and then send you off into the break. So I'm going to go back out. That is not what I meant to do. I'm going to go back a couple of slides. I'm going to run 3 or 4 minutes late, but I want to do this intermezzo now because it links to a nice video that you could watch during the break. This is a story that a colleague of mine really likes. So in this intermezzo, I want to talk a little bit more about P versus NP outside of computer science. P, the set of problems easy to solve. NP, the set of problems easy to verify a solution for. Now here's a nice story. I wonder if you can tell me what this story is about. I'm gonna give you, let's say, these 40 seconds first to read it. Don't post it in chat yet if you know. But after these 40 seconds, feel free to let me know what you think this is about. Okay, so what do you think this story might be about? Any guesses or ideas? Silence so far. I'm going to give you another 5 to 10 seconds to give me a guess if you have one. None at all? Some of these statements are rather obvious. Yeah, maybe. Yes. But what if I tell you that this story is actually about kite flying? Vliegeren in Dutch. Then suddenly, all of these sentences fall into place. If a rock will serve as an anchor, sure, you need a lot of room, birds seldom get close, young children can enjoy it. And this to me is another nice example of one of these problems in NP. Finding what this story is about is relatively hard, but when I give you the solution, look, it's about kite flying, you can relate that to all of these different clues and you can see why kite flying is the solution. Now, this question of problems that are easy to solve versus problems that are easy to verify is still an open question in computer science, right? It is the question of does P equal NP, yes or no? But even beyond computer science, I think P versus NP plays a very important role. In mathematics, for example, a well-written proof is easy to verify. You go through it step by step and you see, does this step make sense as the consequence of the previous steps? But constructing a proof is relatively hard. Now, if it turns out that P equals NP, we could ask a computer, is there a proof of less than 1,000,000 characters for this theorem? And it would output yes or no in an efficient way. So if P equals NP, constructing a proof and verifying one become equally easy. We would all be the next Gauss. In physics, we have a whole bunch of processes going on inside our bodies and in nature that appear to be solving NP problems. I say NP minus P, so problems that we really believe to be hard. Is this true? And if so, how do they do it? Could we not mimic that same behavior? And perhaps even in art, is there a difference between appreciating art and creating it? Between verifying that something is art and between finding new art, right? Finding the solution, verifying the solution. Is there really a difference between these? So this question of does P equal NP has tremendous applications in computer science, but also in mathematics, physics, art, philosophy, and many, many other applications. Many other domains, I should say. Now, because I cannot tell you this in the same amazing way as some other people can, if you want to watch another person talk for a little bit during the break, there is this amazing YouTube video. It's called The Complexity Zoo. I've posted the link in chat as well, that you can watch during the break, and we'll continue this in about 15 minutes. See you in a bit. Right, welcome back. I hope some of you, like me, took the time to once again watch the video on the complexity zoo. If not, then you have a nice 10 minutes to look forward to later today. During the break, some questions came up about P versus NP. I think I've handled those sufficiently well. One more question about the exam came up, about if the grade for the midterm could not be counted on Osiris. Well, so the grade for the midterm I will use in determining whether or not you pass this course. So the midterm definitely was not for nothing. Unfortunately, after discussing the situation with the Board of Examiners and Rick, we have decided to move to a pass-fail system because in combination with this take-home exam, the only guarantee I can really give is that after talking to you, I will be able to establish whether or not you indeed, on your own strength, have been able to do this exam and thus understand the course contents. But in situations like this, the Board of Examiners does suggest moving to, or strongly recommend moving to a pass-fail system instead. Elevated Dutchman is also asking us a question about the exam. So now the grade is determined by the average of the analysis and implementation parts with no minimum to achieve for either. Correct. So any minimum requirement on implementation or analysis has been dropped. Si Jing, is there a way to ask questions during the exam if a question is unclear or if there are any problems? Yes, the WebLab discussions will be open and I will be monitoring my email, so if you cannot even get into WebLab, you can send me an email. I will be available for the full 2 hours during that exam. I'm looking into whether I can set up other communications channels for you to talk to me, but at least email and WebLab will both be available. I can show you tomorrow during the tutorial, if one of you reminds me, how this communication works. I fully agree. It is indeed. I also think it's a very, very big pity that we cannot distinguish between just a pass and people that would normally get a 10. I can only say, I'm sorry, I'm trying to do the best that I can under these circumstances. And I believe a pass-fail is the best we can do here. But my apologies. I don't like it any more than you do. Willemijn, is the interview after the exam only to determine whether you've done the exam yourself, or is the interview also about the course? Good question. So I talked a little bit about this in the announcement. We will be using your exam as the basis for our discussion. So I will ask you questions about the answers you gave, see if you can explain why you implemented something in a certain way, or if I were to change something about the problem, what would happen to your answer, something like this. I will likely also ask you some new questions that are variations on the themes from the exam. As an example, let's take something from the midterm so that I'm really not giving anything away, right? But imagine that, again, this is midterm material, so it's not going to be on your exam. But imagine I would ask you a question about quicksort, you would have implemented it, and now I would tell you, okay, what if I wanted to sort on this instead? How would your code change? Right? So instead of sorting on age, I now want to sort people on length, something like this. And since you've written the code, you should be able to tell me what would be changed. So stuff like this I might ask you. I might also ask you, okay, you implemented, I don't know, a BFS, great. Now imagine I have this graph. I show you a picture of the graph. I ask you, okay, how would your code perform on this graph? You know, stuff like this. Does that make sense, Willemijn? And also, Elevated Dutchman, did I answer your question? Good to hear I answered yours, Siching. So the interview is to determine whether you did the exam yourself, but in order to determine that, I might ask you some questions that are variations of the exam questions. Good. Questions seem to have been answered. Again, I see nothing else, but once more, at the end of today, the last 5 minutes or so, we should definitely have left. So if there are any more questions about the exam then, or if there are any tomorrow, please, by all means, do ask them. I would like to answer any and all questions you have. Okay, one more question from Gideon before we get started. Sorry if this has already been answered, but is the midterm material not also material for the end term? No problem. I did not explicitly mention this today, except in one sentence just now. Is the midterm material not also material for the end term? No. So the midterm material is not part of the end term material. That means I will not ask you to implement quicksort, for example. However, for some problems, we have seen that you require sorting, right? So for example, to do Kruskal's algorithm, you need to sort the edges. So you need to be able to sort things in Python still, and you still need to know that sorting requires n log n time. When we talk about minimum spanning trees, well, minimum spanning trees are trees. So you need to know something about trees in order to reason about minimum spanning trees, right? So I won't ask you questions specifically on that, but questions could require some knowledge, be it about time complexities, be it about something else, from part of the midterm material. For example, you should still know that a linked list has quick insertion at the front of a list, whereas an array list does not, right? These are still things you need to know. Does that make sense, Gideon? Well, I move on to JMDBK. More questions are popping up, which is good. Will there be a way to see your answers during the interview, seeing as there is some time between the exam and the interview? Yes. So I will make sure you can see your answers in DepLab at that time, during the interview. I will be looking at them with you, asking you questions about them, and you will be able to see them too. That actually reminds me, I had a question to ask you. So I've answered Gideon's questions, good. Let's see if I also answered JMDBK's. In the meantime, let me ask you a question. Let's see if we can do that via one of these Twitch polls again. So my question is, and perhaps I should ask it as an open question first, you will likely have more exams next week. How many is that? 1, 2, 5, 8, 25, 2, 3? How many more exams will you have? I reckon it might differ for, oh no, I don't, all of you don't do physics, right? Because physics don't have to do this, I think. 3 more exams, okay. Are these all oral exams? Or are there, or do they have a similar structure to mine? No clue yet. Okay. Okay. 2 more next week, 1 the week after. No information given yet. Okay. Then I think you cannot answer my question. So I'll ask Rick about it instead, which I was going to do regardless, but I hoped you could give me some information. So the question I had is the following. As you know, our exam will be on Monday morning. I hope to finish grading by Monday afternoon at 5. That gives me 6 hours. That should be doable if I put everything else aside. And then I'd like to have the interviews from Tuesday afternoon all the way to Thursday afternoon. So Tuesday afternoon, all of Wednesday, all of Thursday. But I was wondering when or how your other exams are scheduled to see if this is possible or not. I would like, if possible, for our course to be done at the end of next week, especially since I have many other things to worry about after that. But I'll ask Rick then. I'll ask Rick what your schedule is like and when I can steal you for a little bit. Thanks anyway. Okay. One last question and then we get started again. So I'll do more questions at the end. The last question I want to answer from Oh Come On. Is the interview held in English? Well, I speak English, I speak Dutch. Both languages are fine with me. A mixture of both is fine too, right? So if you want to talk about grafen that have vertices, dus er is een graaf met een aantal knopen en er zijn een aantal edges, right? You mix Dutch and English, that's all fine with me. I don't really care. Other languages than Dutch and English will not be accepted. But I will prepare questions in English. I can translate them if you want, but my preference would be English. If need be, I can switch to Dutch. Should I email you if my schedule is different than for most courses who take this course? Only if when I let you know when the interviews are and you cannot make them in these time slots, then you should email me. So await my proposal for times first, and if that doesn't fit in your schedule, SF de Jong, then you should send me an email. Cool. Then let's get back into talking about P versus NP, and we'll save more exam questions to the end. So just before the break, I introduced to you the classes P, problems that are easy to solve, and the class NP, problems that are easy to verify a solution to, where easy means polynomial time. So problems that can be solved in polynomial time, problems that can be verified in polynomial time. And for TSP here, we've seen that we can verify a solution in polynomial time. Now, consider the problem path. Given a graph, two vertices, is there a path from vertex S to vertex T? What do we know about this problem? Is it in P? Yes or no? Is it in NP? Yes or no? Time has started and Feedback Fruits is happy to hear your thoughts. Perhaps 40 seconds was not quite enough. I'll give you a couple more here. Let's say 5, 4, 3, 2, 1. And by the time you hear this, I should now also roughly be at 1, so I can close it. Answer D is the most popular with about 60% of the votes. It is in P and it is in NP. Yeah, well, so we already saw previously that it is in P, right? This question, given two vertices, is there a path from S to T? We can answer with BFS or DFS, runtime V plus E, that's polynomial, so path is in P. That gets us to answer C or D. Is it also in NP? Well, how could I verify a solution? How could I check a solution in polynomial time? Well, if you give me a path, I can check that this is a path from S to T and that this path exists in the graph. So I could do that easily in polynomial time. Or if you say, yes, this can be done, here's the path, I can say, oh, thanks for the path, I don't care. I'll just solve the problem in polynomial time. And if I find a path in polynomial time, then apparently the answer was yes. So I could easily verify the solution, sure. You give me a path, I can verify it. Or I just solve the problem and thereby verify your solution. So with that idea in mind, can we say something more general about the classes P and NP? Is there some relation between them? Again, Feedback Fruits is happy to hear your thoughts, and of course, so am I. Again, I'll give you a couple more seconds here. 18 out of 25 now, we're getting there. And that will do. Let's see. Ooh, very nice distribution. But A and B are the most popular, although E is close behind. So first, let's clear up notation, because you might have learned something different than we use in computer science. So answer A for us represents proper subset. So everything that's in P is in NP, but there is also something in NP that's not in P. And answer B for us represents P is a subset of NP, so everything that's in P is in NP, but they could be equal. Yeah, some textbooks use the same symbol for that, but in the textbooks we use for reasoning and logic, in computer science, therefore there is a difference between A and B. So thanks, Jan. I can imagine that you may have learned that A and B and D and E are indeed the same. We see them as different. But in that case, good, because that means the overwhelming majority is for A/B, which is the right answer, right? I would even say B is the right answer. So P is a subset of NP, meaning everything that's in P is also in NP, but they could be equal. They don't have to be, but they could be. Answer E, the other somewhat popular answer, is the thing we don't know. If that is the case, well, then combine B and E, and we've shown that P and NP are equal, right? But E we don't know. All right, I should hit next in the right screen. There we go. So a proof for this, if you want one, well, take a problem in P, show it's also in NP. Okay, if it's a problem in P, that means we can solve it in polynomial time. So how do I check a solution? Well, I just solve the problem and I compare the solution to whatever you gave me. So P is a subset of NP. Right, for multiplication, for example, if I want to multiply numbers and you give me an answer, you tell me that the video uses 51 times 3, but you tell me 7 times 8 is 56. How do I check that? Well, I multiply 7 times 8 and I verify that it is indeed 56. I just do the work. And I can because it's an easy problem, a problem in P. So P is indeed a subset of NP. It's the other way around, that's the problematic part. Right? So we don't know whether NP is a subset of P. We don't know if they are equal. Now, we think not. And when I say we, I mean computer scientists. An overwhelming majority of computer scientists believes P and NP to be different, to be unequal. But so far, we don't know. We have, of course, been trying to find out. And to do this, we have focused on one specific class of problems. A class of problems called NP-complete problems. They contain, if you will, the hardest problems in NP. Why is that? Well, because problems in NP-complete are in NP, so their solutions can be verified in polynomial time, but they have one extra property, namely that every problem in NP can be formulated as an NP-complete problem. For example, consider the problem of the traveling salesman. Is there a route through all cities back to Delft with a length less than k? We can do some work, some polynomial work, to rewrite this problem as our Max-Clique problem from earlier. Or some polynomial work to rewrite it as the partition into triangles problem from earlier. So by doing some polynomial work, I can take TSP, traveling salesman, and rewrite it to something else. What does this mean? It means that if I find the polynomial algorithm for Max-Clique, then I've also found a polynomial algorithm for TSP. Because I take my TSP instance, I transform it in polynomial time into something, into a Max-Clique instance, and now I solve that instance using this algorithm I found. And that is why the class of NPC is so very nice. If I can show for just one problem in NPC that it is actually in P, then all problems in NP can be solved in polynomial time. Because all problems in NP can be rewritten to that NP-complete problem in polynomial time, and therefore all problems in NP can be solved in polynomial time, proving that P equals NP. And there are many problems in NP-complete. TSP, Hamiltonian path, ordering people so that they are only behind and in front of someone who they interacted with. Free matching and all kinds of other problems are all problems that are NP complete, that are amongst the hardest of the hard problems. You might be asking, okay, but are there problems in NP that are not in P, but also not in NP complete? So they're not amongst the hardest problems, but also not amongst the easiest problems. Again, our answer is we don't know, but we think so. An example of this is factoring. Given a number, given a number n, you ask the question, is there a prime factor of at least k? At least or at most? I think it's at least, but it could be at most. I'm not entirely sure. This problem is in NP. If I give you the prime factor, you can check that indeed this number is divisible by this prime factor, that n is divisible by this prime factor. But we haven't been able to show it is NP complete. We haven't been able to show that every problem in NP can be rewritten as the factoring problem. So is there something that is not in NP complete and also not in P, but still in NP? We think so, for example factoring, but we don't know, because as soon as NP would equal P, so if P equals NP, well, then this thing also becomes just a problem in P. Okay, so we have P, we have NP, and then NPC as the set of hardest problems. Is there in something more difficult? Yes. There is the class exp. And exp is the set of problems that are solvable in polynomial time. And all problems in exponential time, sorry. So exp is the class of problems that are solvable in exponential time. And NP is a subset of exp. There's a nice proof for this that I won't bother you here. It relies on talking about non-deterministic Turing machines. Too complex for this course. But it means that there are problems that are harder than these NP complete problems. Consider a problem that is not in NP, so even if you give me the solution, I cannot check it efficiently, right? It's not in NP, but it can be solved in exponential time. An example of this is playing a game of chess or playing a game of checkers, right? Given the state of an n by n chessboard, if it were 8 by 8, then it would be solvable in constant time even, because there's just only a constant amount of configurations, an enormous amount, but a constant amount. So we need an n by n chessboard. Can the player with the white pieces win in k turns, regardless of what the other player does? Now imagine that you tell me the answer is yes. And you give me a solution. So you tell me this is the move you now need to make. How would I know you're right? How would I check your solution? The only way I can check it is by simulating all the different options that the player with the black pieces could do. But there's a lot of those. Way more than a polynomial number of those. So even checking a solution is not easy. So this problem is also not in NP, we think. This is actually a problem in P space, as we call it. And it is still possible that this problem is also in NP, that NP and P space are equal. We don't know. So, we think so. For example, chess, which is a problem that cannot even be verified in polynomial time, but we don't know. Okay. Now, I told you all the way at the start of this course that this course would be about puzzles and using computers to solve them. Well, I've shown you a bunch of puzzles throughout this course. But as it turns out, many of the things that people often call puzzles are also NP-complete problems. Consider, for example, Sudoku. Sudoku, given an n squared by n squared grid, we need to fill in these numbers. Every row, every column, and every n by n box contains every number exactly once. Can it be done? Right? So given one of these grids, can we fill it out? That is the question. This question is also NP-complete. Given a solution, I can check the solution for you easily. I check every row, I check every column, and I check every square. That's it. But finding the solution, I have no better way for than something that requires exponential time. I have no polynomial time algorithm to solve Sudokus. I don't. If you do, let me know, because it means you have shown that P equals NP. Now Sudoku, but also other puzzles, we skipped this one this year around, but if you represent letters or digits as letters, right? So you could, for instance, have pot plus pan equals bib, dog plus cat equals pig, boy plus girl equals baby. These could be 3 statements. Now we need to see what digit P, O, T, A, and N, and all these others represent. Right? They could be a number between 0 and 9. We need to find out what they are. This is also an NP-complete problem. It's a puzzle you may have seen before. And even some problems in video games like Tetris, Super Mario, and all kinds of other video games have problems that rely on NP-complete problems. That's what makes them challenging. That's what makes them fun. Right? They are hard to do, but once you found the solution, you can be sure that you have the right solution. So, to summarize this, we're going to be done a bit early today. That's okay. The main question we have in computer science, if you ask me, it's our ultimate challenge. The question is there a fundamental difference between problems that are easy to solve, problems in P, and easy to verify, problems in NP? Now, like I mentioned, we believe that P does not equal NP. And perhaps it will be one of you, a mathematician, to finally save us, and solve this problem for us. We've been trying for many years, and so far we haven't gotten there. Now, last year I recommended that you take a course on complexity theory to learn more about this problem. I can no longer do that. Soon there will be a new course that teaches you a little bit more about this. Now we have a course in the master called Advanced Algorithms that you could take if you want to know more about this. I think mathematicians can take it, I'm not entirely sure. But even without all of these courses, these are problems worth thinking about because they deal with so much more than just computer science and mathematics. As I mentioned in today's intermezzo, the difference between recognizing good music and creating it, the difference between recognizing a good teacher and being one. P versus NP is so much more than just a very, very nice computer science problem. And I believe we need you as mathematicians to help us solve this problem. We've been trying and we failed. Perhaps you can help us. And that brings us to the end of this course. Well, we have one more tutorial tomorrow, but the end of all the content that I wanted to discuss with you. No new things will pop up tomorrow. In this course, we've seen a lot. 8 weeks ago, we started with talking about lists. And I talked to you about time complexity. We talked about stacks and queues. We talked about heaps, trees, maps, and graphs. We talked about binary search. We talked about finding the closest pair of points. We talked about all kinds of tree traversals. We talked about shortest paths and traversals in graphs. We talked about finding minimum spanning trees. And today we talked a little bit about the ultimate challenge in computer science. The question, does P equal NP? Now what is left? Well, tomorrow we will have a tutorial in which I have, I think, one old exercise to do with you, and the rest is fully available for you to ask me questions and I will try to give you answers. There will also be lab sessions this week. I think there will just be 2, so this says 1, but I think there's 1 on Wednesday and 1 on Friday. I should check. But there is no new homework for this week. So there will not be homework for this week. There are old exams for you to practice with and to ask questions about. And next week you have an exam. Now, first things first. There's 3 more questions I want to ask of you, and you might have new questions for me in the meantime. First 2 questions are about the course, and they are questions that unfortunately cannot be put into Evasys, so I'll be asking them now. The first question is, what topic did you like most about the course? You will be able to answer in feedback fruits in a moment, but this is to give you already some time to think about it. What is the thing you liked most about the course, or what's the topic you liked most? What is the topic you liked least? And the final question is, what do you want to talk about in tomorrow's tutorial? Now, Om is already asking in chat, will there not be a tutorial on Thursday? So last year, we did not have 2 tutorials in the final week. This year, I wasn't planning on having it either when we were still on campus. Now, I can imagine you might have more questions. So on Thursday, I will be around and I'll be able to ask some questions. I'll even have the Twitch stream up and I will be able to answer questions if you have any. But I hope to answer all of your questions tomorrow. I hope that also answers your question, Om. So there is no plan for a tutorial on Thursday. I will be available for Q&A. Let's put it like that. Okay, let me open up the first question for you in Feedback Fruits. And if you have any questions for me, you can put them in chat in the meantime. So first of all, your favorite topic in the course. What did you enjoy most? I'll give you 2 minutes to type something. There we go. Okay, you have about 20 seconds left. By the time you hear that, it's probably more about 15. Please make sure you've hit send before I hit close so that your answer gets in. Okay, time is up. 5 seconds to account for the stream delay on that. And then I will close the question. Thank you very much for those of you who've answered it. Based on last year's feedback, I've shifted around a little bit the focus on different topics. So maybe I can do the same for next year. While I said that, one more popped in here, but now I am really closing it. Okay, then how about least favorite topic? I again, 2 minutes or so to answer that. I'm not going to discuss your answers on stream. I will read them through later. I think that is a better suited format for that. And again, only a little bit of time to wrap up your answers. Let me see. Okay. Again, thank you very much for those of you who took some time to fill it out. I will be closing the question now, so hit send if you haven't yet. All right. Then, are there things you would like to talk about tomorrow? Now, you can ask tomorrow, of course. Right, that's not a problem. If you just ask tomorrow, I will be happy to answer there. But if, for example, 3, 4, 5 people all indicate, well, I'd like to practice with implementing algorithm blah, then I can actually prepare an exercise on this, right? So tomorrow I can answer questions ad hoc. I have a blackboard, I can write things, I can type things. But to have exercise for you to practice with, I need to know in advance. So is there anything that you would like to talk about tomorrow, that you would like to do tomorrow, anything like that? Thanks for the suggestion also in chat, Browhead. Maybe we can discuss a general strategy of steps you go through to tackle an implementation problem. Yeah, I'll see if I can do something with that. And again, keep an eye on the time. Once I close this question in feedback fruits, there is no going back. If you hit enter on accident, is there a way to change my answer? I don't think so, Gideon. So if you're comfortable sharing it in chat, feel free to do it in chat. You could also send me an email if you're less comfortable discussing it here. Okay. Well, final question. No, well, actually says save that for tomorrow's tutorial. Yeah, that will be fine. Okay. Thank you again for being here today. I will see you for tomorrow's tutorial. That will be the last structured session we have, in which I will try to answer all of the 10 questions submitted via Feedback Fruits just now. I have one other small assignment available to practice with. We'll see how that goes. On Thursday, there will be a Q&A session. If you have any questions, I'll be around. And then there will be the exam next week. If you have any questions in the meantime about the exam or anything like that, please post them on the Brightspace forums. And with that, thank you very much for your feedback and being here today, and I will see you tomorrow. Bye.